All right, now that we have started to define matrices, now we can start to look at some operations with matrices. To begin, we're actually going to work on some notation. So before we've had matrices, a lot of them were like 3 by 4 or 4 by 5 or whatever, no matter what matrix it is. You can use an uppercase letter to define an entire matrix. So instead of having to rewrite a whole 5 by 5 matrix, you can just call it A and then rewrite A. So until you need to work with it and work with the individual entries. And we are going to call two matrices equal if they have the same order, meaning the same amount of rows and columns, and every single entry is exactly the same. If just one entry is different, the two matrices are not equal. But that's pretty straightforward. And actually, I think the addition and subtraction of matrices is... is also pretty straightforward, because to be able to add matrices, you need to have the same order, meaning if it's a 2 by 2, you can only add and subtract it with a 2 by 2. If it's a 5 by 3, you can only add and subtract it with a 5 by 3. And the way you're going to add them, when we add a 2 by 2, the answer is going to, and a 2 by 2, it's going to be a 2 by 2. And what we are going to do, we're going to take first row, first column, we're going to add them together. The answer goes right here. So there's not a lot of work to this. It's just a matter of being careful with our addition. 2 plus 3, we're going to add them. The answer goes right here. Here we're going to add 0 and -1. Add them. The answer goes right here. And last but not least, we are going to add 1 and 2, and the answer goes right here, right there. So that's a matrix addition. Matrix subtraction isn't much different. If you are going to subtract two matrices, we have a 3 by 1 and a 3 by 1. Our answer is going to be a 3 by 1. And what I like to do when I subtract matrices, because I think subtraction's harder, I always like to think of adding the opposite instead of subtraction. So I actually like to change this to a plus sign and then change the sign of every single entry, because believe it or not, I see way more mistakes on matrix subtraction than matrix addition. So I think changing the subtraction to addition and adding the opposite makes it a lot less likely to make those mistakes. So here we are going to have 1 plus 1, and that answer is 2. In the middle row, we have -3 and -3, -3 and -3. That's going to be -6. And in the bottom row, -2 and -2. That answer is going to be -4. Here's our answer as is. If you ever see, this is right here. This is a 2 by 3 matrix trying to be added with a 2 by 2 matrix. It is not possible. No solution. And the reason is, if you think about it, yeah, fine, I can add these up, I can get an answer. I can add these two up, I can get an answer. This one has nothing to add up with, and that's really the reason there is no solution, because the process doesn't work. It doesn't work. It's not possible to add or subtract these two matrices. So we have matrix addition and subtraction. I think that's pretty straightforward. I actually think matrix scalar multiplication. Now, scalar is just another word for constant, all right, just like we learned when we did vectors. A scalar times a matrix is always going to yield a matrix. So what I have here is I have two matrices, A and B, and if you're going to multiply 3 times matrix A, all you are going to do is multiply every single entry in the matrix, all 9 of them, by 3, all right, and what this would look like, your new matrix is going to be 6, 6, 12, -9, 0, -3, 6, 3, 6. All I did is I took every single entry, multiplied it by 3. If I was going to do negative b the same way, well, let's take it -1 and multiply everything in there by -1. So my answer would look something like this. So again, I think scalar multiplication, matrix addition, matrix subtraction are not the hard parts of this lesson. A little bit of practice is needed, but it's really just attention to detail. Here's some properties, all right? Remember, uppercase letters stand for matrices. These lowercase letters, like C and D, those are going to stand for constants. But, okay, Matrix A plus matrix B, that's the same thing as B plus A. I can switch the order, same thing. This is really a commutative and associative properties in rules 1 and 2. 3 is dealing with the order that you do the scalar multiplication. It doesn't really matter. If you want to do the scalar multiplication first or multiply the constants first, you can do either. 1 times a matrix is still going to be the same matrix. You can do distributive property with scalar multiplication. Either add the matrices first and then multiply by the scalar, or multiply the scalar to both of them and then add them. And the same thing, you can actually work the other way and distribute a matrix into an addition of two scalars. So those are all important properties as you work, in which we can use them here. Solve for matrix X. 3 times some matrix plus A equals B. So if you're trying to solve for this matrix, you're going to treat it just like a regular variable. I have 1, negative 2, 0, 3 equals negative 3, 4, 2, 1. And I want to try to isolate my variable in a way I've done before. And to do that, I am going to want to subtract this whole matrix, right? Subtract 1, negative 2, 0, 3. Gets all of this to cancel out. If I do it to one side, I'm going to need to do it to the other. And I prefer to think of it as not subtraction, but adding the opposite, so all those signs change. And now I have this new statement: 3 times some matrix has to equal, let me add these together. That's going to be negative 4, 6, that's going to be 2, and negative 2. And last but not least, to get this matrix by itself, I can think of it, whether you want to think of it as scalar multiplication and multiplying by 1/3, or you prefer to think of it as dividing by 3. They're both mathematically equivalent. It doesn't matter. Matrix X is going to be, well, all I have to do is scalar multiply this out. Everything gets divided by 3. That's going to be negative 4/3, 2, 2/3, and negative 2/3. So there's my 2 by 2 matrix answer using operations to both sides and actually being able to solve for a missing matrix. I know if I took this matrix as our answer and I multiply it by 3 and I add A, I will get B as an answer. That's a guarantee. Okay, so matrix multiplication is definitely the trickiest part of this section. And the way you multiply a matrix, first off, when you multiply a matrix, it's good to mention the order of this. This is a 3 by 2 matrix, and this is a 2 by 2 matrix. Notice the orders are not the same. To be able to multiply matrices, these two numbers need to match. They need to be identical. The number of columns in the first matrix must equal the number of rows in the second matrix. That's what that's really saying right here. So to multiply this, what I'm going to do is I'm going to take row 1 in the first matrix, column 1 in the second matrix, and I'm going to, it's kind of like a dot product. I'm taking negative 1 and negative 3, I'm multiplying them. Negative 1 times negative 3, and I'm going to add 3 times negative 4. So all of those numbers come from what's circled in red. All right, I am going to total that up and get one singular answer. So you think of this as 3 plus negative 12. So this answer is negative 9. That is part of my answer in my matrix. That answer, because I've used row 1 and column 1, that answer goes in row 1, column 1. And now I got to go back and I start over. I can continue to reuse row 1, but this time I will use row 2. So it again kind of looks like a dot product. In this case, negative 1 times 2, 3 times 1. As you do this, you'll probably be able to start doing it in your head. That's negative 2 plus 3. That's going to be an answer of 1. Because I multiplied row 1 and column 2, that answer goes in row 1, column 2. So I can't use row 1 anymore. I'm going to continue to use row 2, column 1. So 4 times negative 3 plus negative 2 times negative 4. So that's negative 12 plus 8. -4. That answer goes in row 2, column 1. My new multiplication here is going to be still row 2. Let's multiply it by column 2. So 4 times 2 plus -2 times 1. That's 8 plus -2. That answer 6. Answer goes in row 2, column 2. Last one, row 3, column 1. 5 times -3 plus 0 times -4. That's going to be -15. That answer goes in row 3, column 1. And last but not least, row 3, column 2. The answer to this one, in the interest of time, I won't write it out. You should be able to get it on your own after seeing it a few times. So here's the part that I'd like you to notice. So I told you that these had to match in order to be able to multiply your matrices. And the nice part is if those match, the matrix that's your answer ends up being a 3 by 2. This matrix right here is a 3 by 2 matrix. That will work every single time you multiply matrices, if you're ever wondering what your order comes out to. Okay. All right, so here's one more quick practice. So let's do one quick matrix multiplication for practice. I actually think this is probably a good one to try on your own and check it with my work. So here we've got row times column. So what I'm doing, -2 plus 0 plus -3. Those are the three. I did the multiplications in my head, and those are the answers I got. So -5 is my first answer. So now I got row 1, column 2. So the numbers that I get when I multiply, 4, 0, and 3. So that answer is going to be, that's row 1, column 2. So I got row 1, column 2. That's where the 7 goes. Let's look row 1, column 3. That's going to be 2 plus 0 plus -3. That's going to be the answer of -1. It goes right here. All right, I have nothing more I can do with row 1, so let's try row 2. Row 2, column 1. -4, -1, and 2. I'm going to add those together. That ends up being -3. My answer goes in row 2, column 1. All right, next column. I'm multiplying 2 times 4. That is 8 plus 0 and plus -2. So that answer is 6. That goes in row 2, column 2. Last one. Bottom row, 2 times 2 is 4. So that's 4. I'm going to get plus 0 and then plus 2. That answer is 6. My answer here is a 2 by 3 matrix, and the reason it's a 2 by 3 is, well, this is a 2 by 3 matrix. This is a 3 by 3 matrix. Well, these ones matched. That's why we could multiply them. And my answer is a 2 by 3 matrix every single time. I will leave you with a few properties of matrix multiplication. Matrix multiplication, A times B times C. If you want to do A times B first or B times C first, that doesn't matter. You can distribute a matrix multiplication, or you could add first and then do the matrix multiplication. Notice this has to be written 2 different ways. Both 2 and 3 look like they're saying the same thing, but if you notice, there is one property that is not up here. AB is not the same as BA. That is extremely important, and that's why 2 and 3 look so similar, because it's dealing with the order that you are multiplying your matrices in. So that becomes extremely important. Last but not least, 4 is saying you can the distributive property doesn't really work with a scalar. You only multiply the scalar to one matrix. All right? And here what we have is an identity matrix is a square matrix that has 1s in the main diagonal. This matrix right here, this is an identity matrix. All right, so the question I want to leave you with is what happens when you multiply by an identity matrix? Try to come to an answer to class tomorrow. I will see you then.